Well, let me introduce our next speaker, Adam Osenkowski, who is a professor at the University of Warsaw. Adam Osenkowski is an internationally recognized expert in Martingale inequalities and Bellman functions. He wrote a large number of papers with delicate, often sharp estimates, and 2 excellent books on the subject. The Bellman method originated from control theory, but then it has reached far beyond its birthplace. In any case, the Bellman method makes use of an auxiliary function. Finding such a function is a part of an intelligent guessing game and requires some experience and a golden hand. And Adam Osenkowski is a world master in that. He has given a number of sharp inequalities without alternative proofs, which means his proofs are the only ones known. In 2016, he was awarded the prize of Polish Academy of Science for his outstanding achievements. This is one of the most prestigious prizes in Poland. Okay, please, Adam, the floor is yours.
Thank you very much for this nice introduction. So, one thing, how can I make this thing? All right. So first of all, let me. I'm sorry. Yes, the recording. Yes. It's being recorded. Yes. So first of all, let me thank the organizers for the invitation. It's a great pleasure to be here and be delivering this talk. So, well, so we'll be discussing some very small portion of the so-called Bellman function method, and I wanted to make this talk as accessible to everybody, and at least the first half of it will be extremely elementary. So I wanted to give you the flavor, the taste of this method on some examples. All right. So let us begin. So, well, generally we'll be speaking about inequalities. Okay, so Bellman function method is the technique which is used for the proof of inequalities in probability and harmonic analysis. All right. I'm still experiencing some difficulties. All right. Okay, so let us say a few words about the history. So it started with a sequence of papers by Richard Bellman in the 50s. His works concern the theory of optimal control. And in 90s, Donald Burkholder noticed that this method developed by Bellman can be used outside stochastic analysis. Okay, he noticed that one can prove some Martingale inequalities. He also applied this to some basic properties of the so-called Haar system. And in the mid-90s, decisive step was made by Nazarov and Goldberg, who showed that this method can actually be used for a wide range of problems in harmonic analysis, very general range. Okay, and nowadays this method has been implemented in many contexts. Okay, maybe one comment here is that essentially, there is no meta theory of Bellman functions. In a sense, this is like that. This method can be applied in several specific directions, and for each direction, one has to develop the Bellman method separately, in a sense. Right? So there's no unified treatment. But anyhow, we'll try to give some general tricks. And which are used in all these directions. All right. Okay, so what is the rough idea? Okay, so suppose you want to prove an estimate just of this form, u smaller than v, where u and v are some quantities, possibly, well, quite complicated. Well, so the idea is like this. Well, so if the Bellman method is applicable, then it returns a certain sequence Wn, such as we see here, right? So it returns some intermediate sequence Wn, which can be inserted in between these two expressions, right? So of course, well, if we manage to insert such a sequence, then this inequality we want to prove holds true, right? So these terms Wn are expressed by this Bellman function method, by means of a certain special function which is called the Bellman function associated with a given estimate. Okay, and well, as we'll see, this function must satisfy certain size, monotonicity, and concavity properties. Okay, so that this chain of inequalities holds. Okay, so you see that the rough idea is trivial, right? You want to prove an estimate. The idea is to insert something in between. Okay, and these things in between must depend on the special function. Okay, all right. So the plan is to discuss, well, 4 topics. So first we'll deal with a certain very elementary inequality. Then we'll try to discuss some aspects of Dub's maximal inequality for Martingales. Then we'll turn to Martingale transforms and the space of functions of bounded mean oscillation. And then, if time permits, we'll discuss some extensions and further applications. Okay. So let us turn to this elementary estimate. Okay. So, well, this is a very, very nice and simple inequality. So it says the following. So you have some positive integer n. You take some sequence of numbers, sequence a1, a2, up to an. Okay, you assume that these numbers belong to 0, 1. Okay, and here's the inequality you want to prove. Of course, well, there is nothing special about this inequality. This is a very simple inequality. One can show it using different methods. The nice thing is that one can also prove it using Bellman functions. And actually, you will see most of the problems which one encounters in a general situation. So it's a very good training example. Okay. Okay. So, well, the first step is to divide both sides by the right hand side. Okay. The expression on the right here, okay, is positive, so we can divide it and get the equivalent, the formulation. Okay. So we'll try to show this estimate. Okay. We write this. Okay, so the Bellman analysis, well, it consists of several steps. Okay, the first step is to identify the objects which govern the inequality. Okay, so, well, of course, we see here, right, that, well, there are two nice expressions, right? The first nice process is just the numerator. Okay, and the second one is, well, appears twice in the denominator, right? So let us distinguish these two processes, these two sequences, and let us call them xn and yn. Okay. Okay, then of course this desired inequality can be expressed as xn 1 minus yn plus 1/2 yn squared smaller than 1. Okay. Okay. Okay, so it has vanished. Okay, we introduce this sequences x, n, y, n, and let us, for the sake of convenience, let us also extend them to the starting position. Okay, we add some artificial starting point x0, y0. Okay, well, then this is usual, right? We set the empty product to be equal to 1. Okay, and the empty sum to be equal to 0. Right, this is the usual convention. Okay. Okay. What can we say about these sequences? Well, so first of all, they take values in a certain domain. Let us distinguish this domain. So it's denoted by O. So this is just the strip 0, 1 times 0, infinity. Okay. We could work here a little bit more and well, let's restrict this domain slightly. Right, this xn and yn, they satisfy some inequalities also, but, well, for the time being, let us say that this is our domain. Okay. Okay. And also observe that these two sequences, they enjoy the following dynamics. Okay, xn plus 1 is obtained from xn by multiplication, yn plus 1 is obtained from yn by addition. Okay, so we have this nice dynamics. Okay. And the Bellman, the idea of the proof, right, the Bellman proof, is to insert some special sequence. Okay, and here we see this on the slide, right? So what we want to do, we want to insert these special values. Okay. Okay. So what we want to do, we want to find the function. This is the Bellman function. Okay, which composed with this sequences x, n, y, n satisfy this chain of inequalities. That's the idea. Okay, all right. So, well, of course, also how to find such a function. Right? That's the point. Okay, all right. So let us try to list its properties. Okay, so first of all, observe that this Bellman function evaluated at 1.0 is less than 1. Why is that so? Well, this is clear, right? If we want this thing to hold, right, then we know that x0 is equal to 1, y0 is equal to 0, right? So first of all, this Bellman function is this nice function. Well, it must satisfy this first condition. Okay, this first condition takes care about this inequality. Okay, second property takes care about this first inequality. Okay, so this is just this majorization. Okay, this is everything. All right, and the most difficult part, essentially in general, is to find a condition on the Bellman function which guarantees that this intermediate inequalities here, here, and so on, here hold. That's the point. Okay, and this is governed by the third property. Okay, namely for any point from the domain and any number in 0, 1, we have this estimate. Okay, and observe, indeed, if we have this property, right, if it holds, then these intermediate inequalities, right, in the middle here, they hold true, right? This is clear, right? If we just take here, no, if we take here xk, yk, and take ak plus 1, then this is precisely one of these inequalities in the middle, right? Okay, so you see, if the function b satisfies these three conditions, then this desired inequality holds. And we have this whole chain of inequalities and we are done, right? Our inequality is proved. Okay, if only b satisfies this set of requirements. Okay, of course, there's a question. Well, does such a function exist? It's absolutely not clear that such an object exists. Okay, well, and this is the weak point. I mean, I said at the beginning that the Bellman function method has to be developed independently, separately, in various directions, right? So this is the point which needs to be checked in each context. Okay. Okay. Well, in our situation, well, the answer is affirmative. Okay, and let me explain a little bit what happens here. So the statement is like this. So if we know a priori, if we know from some other reason, if we know that the estimate, the desired estimate holds, if we know this, then one can write down the abstract formula for the Bellman function. Okay, so what happens here? So you can take, because you can define a function b, okay, which is given as the supremum of these expressions, where these expressions here are slightly different from the previous ones. You see, here we have these modifications. Okay, so previously we had that x was equal to 1, y was equal to 0. Okay, so what we do now, we extend the problem. Okay, so instead of, if we just put here x equal to 1, y equal to 0, then we obtain just the original problem. What we do, we extend it to a general starting point, xy, right? Take like here. Okay. And we plug it under the supremum and try to compute it. Okay. Well, it returns something. Well, it is some sort of function, and it turns out, right, that this function has this desired properties. Okay. And well, there is no logical error here. I mean, if the desired estimate holds, then the function it's actually this statement. It says that the validity of this estimate is equivalent to the existence of the function which satisfies the three properties. Okay, so this is equivalent, right? If you want to have the inequality, you need to find the function, and vice versa. Okay. All right. So okay, so this was the second step. The first step was the variables, right? The special sequences. Second thing is to see whether this Bellman setup works. Okay. And the third part is the most interesting, actually, I think, right? Well, one has to think about, well, so we see, right? We want to have this estimate, we want to prove the estimate, we need to find the function. Okay, so the question is, what is the function, right? How to find it, how to construct it. All right, so of course, maybe I will say one thing, namely, in some cases, in some particular cases, one can use this abstract formula here. One can actually guess what are what these extremal sequences xn and yn here are. One can guess this. Okay, one guesses the extremal sequences, obtains some function, and then checks whether this function has all these properties. This is one of the possible approaches, but no, we'll go other way. So okay, we start with property 3. Okay, this desired function b must satisfy this condition, okay, as on the slide. So what can we do? Okay, so we see that, well, if we plug a equal to 0, then of course both sides are equal. So we see it. So therefore, if we differentiate with respect to a, then this derivative must be non-positive, particular, right? This is one of the consequences. Okay. Okay, so if we differentiate and compute, we obtain this estimate. It's easy to see. Okay, so if the function b satisfies the third condition, then it must satisfy this differential inequality. Okay, and we'll let us call this infinitesimal version. of this third property. Okay, so you see this is the partial differential inequality of first order. And now let us guess, let us assume that we have equality here. So let us assume that this sum of the partial derivatives is equal to 0. Okay, all right, so then we can solve it. We obtain that this b must be expressed in such a form for some unknown function phi. Okay, all right, so this is the consequence of the property 3. Okay, so now let us go to property 2. So that was one of these majorizations. Okay, so we know that, well, this desired Bellman function b must satisfy this inequality. Okay, so from the previous step, right, we know that this b expresses in this form. Okay, so we get this inequality. Let us plug y equal to 0. Then this reduces to this estimate. Okay, and let us assume equality. Okay, then we get phi of x equal to x, and this leads us to this Bellman function. Okay, all right, now one could protest, right? There were so many guesses, additional assumptions, right? We differentiated this function somewhere in between, right? But a priori we do not know whether this function b is differentiable. We do not know anything about this function. The thing is that this is fine, right? This third step, this search for the Bellman function is informal. The purpose of this step is just to guess the candidate for the Bellman function. Okay, that's the purpose. Okay, so we can assume whatever we want, right? We want to end up with something, with some function, and then once we get this function, well, we need to check whether these conditions 1, 2, and 3 are satisfied. Okay, so in our case, one can easily check that this is the case. So this function is indeed the Bellman function corresponding to the estimate, and this estimate is true. This completes the proof. Okay. Okay, so there another very natural question is, maybe one comment more here. So, well, but of course sometimes it happens that we get some candidate, we start checking these conditions, and some of them fail. If this is so, then we have to go back. We have to go back and think about other candidates. This means that some of our assumptions we made were wrong, were incorrect. Okay, so we have to start over this search for the candidate. Then we obtain another candidate, we check these conditions, maybe these conditions hold. If they do, the estimate is true. Okay, but anyway, in our case, this function works, so the estimate holds. Okay, the next natural question is whether this Bellman function is unique. It turns out that no. For example, this function works as well. Okay, so this is just a theoretical remark. Okay, so in particular, it also implies that if we take the convex combination of these two functions, and this is also a good function. Okay, so the Bellman function in general is not unique. Okay, that's the bottom line. Okay, so let us summarize what we have achieved so far. Okay, so we see that if we have some estimate to prove, right? Okay, so then we split the analysis into the following steps. So first, we identify the processes which govern the inequality. Okay, then we write down this chain of inequalities and see what these properties of this Bellman functions must be. Okay, write down these requirements for the Bellman function. Then we try to find the candidate. Okay, and once we have this candidate, we verify whether this candidate satisfies the set of requirements. And that's it. Actually, that's the general setup, which actually can be used in various contexts. Right? It worked fine for our inequality. It works also for other contexts as well. Okay. Well, just one additional comment. Well, so yes.
Is there Is there some general way to check whether such Bellman function exists in given conditions? Like we want to check existence.
Yes. Well, so as I said, you know, you have to check this. You have to write down. Yes, this is a very good question. So actually, what you have to do in general, it's like this. So the inequality you want to prove typically is equivalent to the computation of some supremum. Okay, like in our case, right? Was that some supremum was less than 1, right? Okay, then this what you need to do is you have to extend this problem, okay, to the general starting point, whatever this means. You know, it depends on the context you are interested in. You have to somehow extend it to various starting points. You may think about Markov processes if you like them, right? This is related to the theory of Markov processes. But this is how this works. So the original problem is to compute or estimate some supremum. So then what you do, you write the same supremum, but for general starting points. If the starting point is xy, you denote this supremum by b of xy. Okay, then you get the abstract Bellman function. It's just some supremum over something. Okay, and well, and this typically this is the abstract Bellman function. This is the typical proof that the Bellman function exists. Okay.
Okay, thank you.
So, all right. So the comment is that sometimes, well, you cannot prove anything like with Bellman functions. Okay, it's not universal, unfortunately. But it's, you know, but it's do not worry. It's not time wasting. I mean, it's if you have an estimate which cannot be proven by Bellman functions, you will not spend much time on that. I mean, it's clearly visible from the very beginning that no, this estimate will not be proved using Bellman functions. Typically, this first step or the second step is not true. There is something wrong with these variables. There are some problems with getting appropriate variables, or if you get these variables, then the evolution of these variables is somehow crazy. It's clear that if you experiment with some estimates, you see that many of them, well, they cannot be studied with the use of the method. Okay. All right. The second. So now we'll try to attack Dup's maximal inequality for Martingales using Bellman functions. Okay, so I will recall some basic facts from Martingale theory, in particular recall some basic definitions. So okay, so we start with some probability space omega fp equipped with some filtration, so increasing sequence of sigma fields. Okay. We assume that Fn is a martingale. Martingale, it means that the following. No. Okay, that the following identity holds for each n. This is a definition of a martingale. Okay. So this is a sequence of integrable random variables which satisfy this condition. Okay. All right. So alternatively, we can define it as follows. So first, one can define the differences. Okay. So if you have some sequence Fn, okay, then you can define the set of differences or increments of the sequence. Okay, and then actually the definition of the martingale is like here. So what I mean that the martingale can be defined either by this requirement, okay, or alternatively, you may think of martingale as a sequence of partial sums of this form, okay, where the summands are conditionally centered, okay. So this is the alternative manner to think of Martingale. Okay. This is a Martingale. I will give one example in a moment. So we'll assume that this Martingale is simple. This is a technical assumption. That we'll assume that all the variables take only finite number of values to avoid integrability problems. Okay, and let us introduce the Martingale maximal function. Okay, this will be denoted by f star, which is given by this formula. Okay, so f star n is the running maximum up to time n. Okay, and of course this maximal function dominates the Martingale. Okay, and this fn star, it's a non-decreasing sequence of random variables. Okay, all right. So maybe let me give a concrete example. This is how one should think about the Martingales if one is interested in some analytic applications. So let us take very concrete probability space, so just an interval with Borel subsets and Lebesgue measure. Okay, and let us consider just some filtration. Okay, so so what I write, what I draw here are the atoms of the filtration. So we have F0. Okay, so this is 0, 1. Okay, so F0 is just the trivial sigma field. The only atom is the full interval. Okay, F1 you see here we split into 2. Okay, so there are two atoms. This sigma field is more complex. And F2 is we split the first red line segment into 2, then we split. Okay, so we look at filtration as a sequence of atoms. Okay, okay, so this is such a filtration, and it is a well-known fact in Martingale theory that if you take any integrable function, integrable random variable, and you consider the sequence of conditional expectations, okay, then you get the Martingale. Okay, so such an object is a Martingale. So actually, in all the analytic applications, right, one should think about Martingale in this manner. Okay, so maybe let us draw some pictures to get some intuition, additional intuition. Okay, so if you have some starting function f, okay, and so you want to find how the Martingale looks like, okay, so then what you have to do. So okay, if you want to compute the random variable f0, the first variable of the Martingale, so then you have to compute this conditional expectation, but F0 was trivial, right? It was the trivial sigma field. The only atom was the full interval. So this means that this F0 is a constant random variable which is equal to the average, to the expectation of the random variable, right? This is F0. Okay, what is F1? Well, the procedure is as follows. So you take these atoms of the filtration of the sigma field, okay, and then you take the average over this atom. Okay, so here this, for example, this line segment is just the average over this part. Okay, all right, and so on. Right, if you take the F2, then you have 5 atoms, and you compute the averages over corresponding atoms. Okay, this is the Martingale. Okay, and you can continue like this. Then you have F3, F4, F5, and so on. This mesh, right, tends to 0. This line segments are finer and finer. Okay, and then what you see, you get, well, a collection of intervals, right? So you get a sequence of functions which approximate f, right, more and more accurately. Okay, so this is the way how to think about the Martingales. Okay, so these are just some partial averages. Okay, all right. So that's the intuition about the Martingale. And one comment more. So the maximal function. So if you want, for example, to compute f2 star, what you have to do, you have to take the maximum of f0, f1, f2. And then you get some other function. Okay. So now the inequality we'll be interested in is the Dup's maximal inequality, which asserts that the norms of the maximal function and the Martingale are comparable, okay, up to the constant p over p minus 1, okay? All right. So what would maybe one comment here is that what we do, we assume here, this is just the technical assumption, it's not restrictive at all, actually. We assume that this martingale is positive, it's not negative, okay? Okay, so we'll prove this estimate using Bellman functions. And well, so first let us rewrite this inequality in a slightly more convenient form, like here. Okay. Okay, so we'll prove this estimate using Bellman functions. Okay, so actually let us be a little bit more ambitious. Okay. And let us try to prove this estimate with some constant CP. Okay, maybe we'll manage to get below P over P minus 1 if we are lucky. Let's try. Okay, so we fix some constant CP. We look at this estimate as on the slide, right? And we try to prove it. Okay, using Bellman functions. Okay. So well, we follow the path we already know. Okay, so well, first we have to identify the objects which govern the inequality. Well, this is clear, right? Here there are two objects, martingale and its maximal function. Okay, then well, it's directly from the definition we see that f0 star is equal to 0. Okay, and we can write down the appropriate domain. Okay, so we see here this is the conical domain, right? We know that the martingale is positive, so x is bigger than 0. Okay, and we know that the maximal function dominates over the martingale, so this gives us the second inequality, x smaller than y. Okay, x and this is y. Okay, so we get some sort of domain which looks like this. Okay, this is the domain. Okay, and let us try to understand the dynamics. Okay, so the Fn is obtained from Fn by adding the increment. This is just the definition of the increment. Okay, and the maximal function, okay, the dynamics is a little bit different. It's obtained as the maximum of Fn star and the next variable. So this is the dynamic. This is the dynamics. Okay. So we have identified the objects which govern the inequality. Now let us try to see if the Bellman setup works. Okay. Okay. So the idea is like previously, we try to insert this additional sequence. Okay, in between. Okay, and well, let us try to identify what properties that this Bellman function must have. And we do, well, the same thing as previously. Okay, so you see, we already said that f0 and f0 star are equal, right? So if we assume here this property 1, then we have this condition, right? Next, the second condition, second majorization, it takes care about this inequality. Okay. Well, and there is also a third condition, which is slightly more complicated, which is responsible for these intermediate estimates here. Okay. And this condition, let us read this. Okay. So what happens here? So we take any point from the domain, we take any simple random variable, which is positive, okay, and has average x. Okay. What we want to do, we want to have, no. We want to have this estimate. Okay. Okay, I will not go into details. So, well, one has to think a little bit about this. Actually, this third condition, it guarantees that this intermediate estimates hold true. Okay. And the good news is that one can show this. We'll not go into details here. That actually we also have the reverse implication. If we know that the estimate holds, then one can construct a Bellman function. One can give an abstract formula for the Bellman function. Okay. So again, the validity of this estimate, okay, is equivalent to the existence of the function, which has these three properties. So actually, at this point, now we can forget. We can forget it about martingales, about everything. We are only interested in the construction, in the identification of this function b, which has these three conditions, right? So we have reduced this problem, proving this estimate, to the search of this Bellman function. Okay, so the point is, what is the formula for b? How to find this function b? If we find it, then we will be done. Okay. Okay, so let us try to find this candidate. So we start with the observation that, well, Dup's inequality is homogeneous of order p, right? So this hints, right? This indicates that maybe the Bellman function also should be homogeneous. Okay, so let us assume this, right? As previously, here we search for the candidate, we can assume everything, right? Of course, the risk is that the candidate we construct will be incorrect, but well, let us not worry about this. Okay, so we assume this homogeneity of the Bellman function, and as previously, the crucial part is the understanding of this third condition. Okay, this condition, well, we already discussed this previously. Well, maybe one comment here. If you look at this, you see that, well, this is some sort of concavity, right? For example, if you forgot about the second variable, right, then this would be just concavity with respect to the third variable, right? Okay, so this is an informal comment, right? The thing I want to say is that this third condition is some sort of concavity, some weird concavity of the Bellman function. Okay, so what we do, we compute the infinitesimal version. Okay, so what we do actually first, so you see what happens here. We first assume that x is strictly below y. Okay, strictly below, and we take a random variable x, which is very close to x. Right, this psi is very close to x. Okay, so that this inequality holds. Okay, we have x, we have y, and we take this random variable very close to x. Okay, then this condition is this previous inequalities of this form. Okay, so this is precisely concavity with respect to the first variable. So this brings us this first inequality. Second, we take the point at the diagonal. We take x equal to y, and again we take a random variable which is very close to x. And actually, what we do, we converge it. We converge with this variable to x. Okay, so we shrink it to x. Okay, it's easy to see that this estimate, if we plug it here, and we perform this limiting procedure, we obtain this estimate. Okay, so the infinitesimal version, okay, of this condition 3 consists of two conditions, right? Here we have the condition of second order, right? The second order derivative, and here the first order derivative. We have two requirements, two partial differential inequalities. Okay, what we do, of course, we assume equality. Okay. All right. And now we know that the function is homogeneous. It's linear with respect to variable x, and we have this condition on the partial derivative. It's easy to compute the Bellman function. It must be of the following form. Okay, where alpha is some parameter which we found in a moment. Okay, so we see this Bellman function. Okay, so this is the Bellman function, and now we move to condition 2, to this majorization. This is the condition. Okay, now what we do, we plug some special values of x and y. We take x equal to 1 and y equal to p over p minus 1. Then of course Bellman function is equal to 0 then, right? If we plug these particular values, and this expression in the brackets vanishes. Okay, so if this is 0, right? So then you see x is equal to 1, y is equal to p over p minus 1. If you plug it, you obtain this inequality, right? So this explains, in a way, why this constant p over p minus 1 appears in Dub's estimate. Okay. Okay, so let us take Cp equal to p over p minus 1, and let us go back to this majorization. Okay, and it's easy to see that, well, the only choice which works is alpha equal to p. For any other alphas, this estimate will fail. Okay, so we are done, right? We have found the candidate. Okay, and now what we have to do, we have to check that this candidate satisfies 1, 2, and 3, and this can be done. So the inequality is proved. Okay. Okay, so again, one can ask about the uniqueness of the Bellman function, and the answer is negative. Again, there are many Bellman functions. For example, well, we have a quite complicated one here. Okay, so if we have this, maybe I'll make one drawing here. So this Bellman function looks like this. So we have this line here, y equal p minus 1x, and you see on this right part, right? This is precisely this first formula. Okay, so on this right part, we have this function, right? And on this left part, we have a different expression. Okay. Anyway, so the bottom line here is that, again, here the Bellman function is not unique. Okay. Okay. Anyhow, so this establishes the estimate of. Okay, I think it's a good time for further. Yes.
Yes. Last question. Is there some special kind of inequalities when the Bellman function is unique? There is like no other one.
This is a very good question. How to answer this? Well, I would have to go into some stochastic details. Well, in general, the answer is that for some type of inequalities, the Bellman function is unique, but this uniqueness is characterized by some behavior of some special stochastic processes, and that's it. Actually, it's if you have some inequality and you ask whether the Bellman function will be unique, right? Then it's absolutely not clear, right? You have to perform this whole analysis. There is no magic key which will answer this question, right? So I think that I'm not sure whether I answered the question.
More or less.
Okay.
Okay. Can you hear me? Or yes? Okay. So are there maybe other questions for this part?
Maybe.
Please take the other mic.
Okay, so maybe this is a similar question to the question the first question that you wrote, and it was asked how to search for Bellman functions. Are there any other types of methods for searching for Bellman functions? Like, for example, you consider a family of functions that satisfy, for example, 3 or 4 conditions that you want, and you use, I don't know, topological facts or functional analysis to simply show that this family is monentous, and you don't find a nice expression of this function, a formula for it, but you simply prove the existence. So some non-constructive proof.
Wow, this is a perfect question, actually. Yes. This is, and this is a huge question. I mean, okay, so let me answer this. Okay, so the methods are the following. So some of them we already discussed here. So the first method is to guess the formula from this abstract expression, right? The supremum over some expressions. And well, in some cases, one thing that, well, maybe this choice is optimal, this choice is optimal, this gives you the Bellman.
The second method is basically the same, but with X aspects.
Yes, but but here there are some differential inequalities. This gives you some additional hints. Okay. Of course, the next method is, comes from experience, right? If you know for example, if you have proven 10 inequalities and you are interested in the 11th, right? Then you can somehow combine these functions, right? And obtain. Okay. The next method, I think it's related to your question, is the following. Okay, so let me think. So sometimes it may happen that we have the following thing, that we want to prove some estimate. Okay, we want to find this Bellman function, but we cannot do this. Some trials that do not work. So what you do, you consider some other inequality. Okay, consider some other inequality which you know a priori that is valid. Okay, which is valid for some other reasons. If it is valid, then it has the corresponding Bellman function, which is abstract. We do not know how this Bellman function looks like, but we know that this exists. Okay, and then you use some sort of manipulations with this abstract Bellman function, and you obtain the Bellman function for this initial problem. Okay. For example, like combining, we take this Bellman function, we take some minimum, something like that. Minimum of concave functions is concave. So you may hope that you obtain here something reasonable.
Okay, this is nice.
Yes, it is.
Okay.
I must say that it's very nice because it is mostly about differentiating functions and statistics. In other contexts, I don't find it interesting, but you made it interesting for me, so thank you.
Oh, okay. Well, not yet. I mean, you have the second part.
Just wait for the second part. Do not.
Maybe some other questions at this moment. Okay, if not, so let's reconvene at 12:15. Okay. Now stop. Not stop, tylko zatrzymać, tak? Tutaj. I tu jest pause, to jest to.
All right. So now we turn our attention to different contexts. So now we'll discuss the applications of the Bellman function method in some other research directions. So we'll discuss Martingale transforms and the space BMO, the space of functions of bounded mean oscillation. Okay. Okay, so we start with definitions. Okay, so what type of objects we'll be using? So again, let us assume that we have some probability space, we have some filtration, discrete time filtration, and now we assume that we have two martingales. Okay, we have a martingale Fn, we have martingale Gn, which are both adapted. And we also assume that we have some additional deterministic sequence Vn, a sequence which takes values in -1, 1. Okay. And we say that G is the transform of F by V. Okay, if we have this identity. Okay. So we already know that, well, this first identity, it's true always, right? It's just the definition of the increments, right? But you see what is important here is that, well, that this expression here, right? This is the nth difference of G. Okay, so you see that this case difference of G is equal to Vk times the case difference of F. Okay. Anyhow, so we see, well, this word transform, I think it's a very good name for this operation which occurs here, right? We have this F, which is written as the sum. okay, and the G is obtained by transforming this sequence. Okay, just one comment. This operation of taking the transform of a martingale, this is just the discrete time analog of stochastic integral. Okay, so this is just a comment. Okay, so then there is some deeper connection. Okay, all right. So what we are going to do, we are going to discuss the inequalities between f and g. Okay, perhaps first let us observe that if we have the situation like here, right? If g is the transform of f, and we know that the sequence v, this transforming sequence v, is bounded by 1 in absolute value, okay, then we have this estimate. Okay, we will use this observation later. Okay, this is just a small comment here. Okay, anyhow, so we consider the Martingale transforms. Okay, and here I will describe this Bellman function method in full generality. Okay, so what you do, you consider just some general function v. Okay, general function v on r squared. Okay, so on the plane. Okay, and suppose that you are interested in the estimate of this form. Okay, so for example, you can take the function v, which is equal to, for example, something like this. Okay, and you see, if you plug this function v here, then you obtain the moment estimate, right? Moment, the estimate between the moments of f and g. Okay, you can take some other functions v, and this turns this inequality here, right, into some perhaps interesting, possibly interesting estimate. Okay, so we have a very general inequality. So and we assume here that f is a martingale and g is its transform. Okay, so Bellman function method says the following. So actually this can be obtained by repeating this argumentation. Okay, I will not do this. Just there is nothing new here. Okay, it turns out that, well, that the validity of this estimate here, okay, is equivalent to the existence of the Bellman function. Okay, so well, we already know this. And what are the properties of this Bellman function? Okay, so well, these first two conditions are just appropriate size inequalities, which control the first inequality and the last inequality. Okay, and the interesting thing, perhaps, the thing which is new in a sense, is this concavity condition. Okay, you remember previously for the Dupes inequalities that this condition was kind of a little bit weird, some weird inequality, weird concavity. Here, this concavity is much nicer. You see, B have that this B must be concave along any line of slope lying in -1, 1, right? Okay, so maybe I will make a picture. So if you have a plane, okay, so the concavity, the special concavity for the Bellman function here is like this: that if you take any line of slope which is not bigger than 1, of slope which is between -1 and 1, okay, any line. Such a line or such a line or horizontal line, whatever. Then this function b is concave along such a line. Okay, that's it. Okay, so if you want to prove this estimate star, you have to find, this is equivalent to the search for the finding of the function b, which has these 3 requirements, right? Which with this funny concavity condition. Okay, and there is a theorem which was proved by Burkholder in 1984, which says that we have the following moment estimate. So we assume that f and g are martingales. G is the transform of f by some deterministic sequence with values in -1, 1. Then it turns out that we have this comparison of the LP norms of f and g. Okay, the LP norm of g it's not bigger than the LP norm of f times some constant. Here we have some very nice and well, strange constant p star minus 1, where p star is just the maximum of p and its harmonic conjugate. Okay. And it turns out that this constant is optimal. Okay. So actually this constant will appear in a moment in a slightly different context. Okay. Anyhow, this is a very nice result. Actually, this result holds true for in the more general context. You remember we discussed this, that if we have this context of Martingale transforms, then we also have this weaker condition. Okay, this condition is called sometimes the differential subordination. Okay, and it turns out that under this weaker requirement, and here, okay, it turns out that this estimate is also true. Okay. So we have a very nice result for Martingale, right? We know that the increments are controlled appropriately, like here, right? The increments of G are majorized by the increments of F. And then if we sum these increments, then G cannot be too large in comparison to F. Okay, so this is a beautiful result. It has numerous extensions. You can consider other sorts of inequalities for other kind of processes. And also,
sorry, may I interrupt with a question?
Yes.
So the question, what happens if this deterministic sequence has values in some larger interval?
Then this constant changes. So, for example, if you assume that this V, right, takes values in some interval AB, then we have some simple scaling of the constant. But if you do not assume reasonably about this value of B, then it can happen that this inequality holds. I mean, it does not hold, right? Then this constant must be infinite. Okay. All right. And well, just one comment. Okay, so this estimate was proven by Burkholder with the use of Bellman function method. And here's the Bellman function. Okay, so we see a very nice, beautiful function, right? Actually, you know, this function appears quite surprisingly in some other areas. Very nice thing. Okay. So now we turn our attention to another context, the context of BMO spaces. Okay, where BMO is just the bounded mean oscillation. Okay, so let me give some definitions. Let me recall the notions. So what we do, we fix some interval. Okay. So I will discuss this context in a one-dimensional version only, but this can also be studied in higher dimensions. But we'll restrict ourselves to dimension 1. Okay, so we fix an interval, and we take a square integrable function. Okay, so function L2, and we say that this function has bounded mean oscillation, or belongs to the space BMOI, if the following requirement holds. Okay, so what happens here? So first of all, this Fj is just the average of F over J. Okay, so what happens here? Okay, so actually here we have that this function has bounded mean oscillation. Okay, so let me make a picture. So we have this base interval I. Okay, so what we do, we take, okay, and we have this for some function. Okay, so what happens here? We take some subinterval J. Okay.
So this is not a subinterval.
Subinterval. Yes. This is subinterval. Yes, subinterval. Yes. Mhm. You take subinterval, you compute the average of the function over this interval. So we obtain something like this. Okay, and now what you do, you take this, you look how this function oscillates around this average, right? So you see, you look at this function here, right? And you integrate this oscillation, right? So here we have this difference between f and this average. Okay, so you have taken this difference and you compute the segment norm. Okay, so the definition, and so the definition might look a little bit weird, but it says that if this function belongs to BMO, if this oscillation is bounded, right, uniformly in J, right? If you take the supremum over all possible subintervals, then all these oscillations corresponding to different J's, they remain bounded. Okay, so these are functions of bounded mean oscillation. Okay, this is the definition of the space BMO. Okay, so the intuition is, well, that this is just another very important space, very important space in harmonic analysis. Okay, we have LP spaces, spaces of continuous functions, Sobolev spaces, and so on. BMO is just another very important space. In a sense, it is in some cases, it can be considered as a convenient replacement for L infinity, in a sense. But I will not go into details here. Okay, so, all right, and here's a very nice result. Okay, namely, you see, we started with a square integrable function, okay, the function which belongs to L2. Okay, it turns out that if it has bounded mean oscillation, then this function is exponentially integrable. Okay, it has very strong integrability properties. Okay, so this exponential integrability is the so-called John-Nirenberg inequality. Okay, and here we have a sharp version of this inequality. Okay, so we have that if we have a function which has bounded BMO semi-norm, okay, and we have some normalization condition, okay, that the integral of f is equal to 0, okay, then as you see, we have this nice inequality, okay, for c smaller than 1. Okay, so you see this constant explodes if we let c go to 1. Okay, so we have this sharp exponential estimate for BMO functions. Okay, and this estimate can be proven with the use of Bellman functions. And let me briefly say a few things about the proof. So, well, the idea, well, it goes through several steps. So first of all, one can show that if you have a function, BMO function, okay, then one can construct a certain pair of martingales. Okay, so start with this BMO function. The idea is that then you can extract, construct a certain pair of martingales, f and gn, okay, which take values in some parabolic region. Okay, so what is this region O here? This is, you see, this is just some region which looks like this. Okay. Here is y equal y. Okay, so this is okay. So this is the first step. Okay, so, well, I do not have time to explain all the details here. The construction is quite involved, but anyhow, so any BMO function gives rise to a certain martingale pair, which lives in a, well, non-trivial set, right? Observe that this set is not convex, right? So it's problematic from some point of view, but later. Okay. So first, we relate this to martingales. Okay, then if we go to these martingales, it can be shown that, well, it suffices to prove the corresponding martingale inequality. Okay, and it turns out that this inequality is perfect for Bellman functions. Okay, turns out that this special function B needs to satisfy the following three requirements. Okay, so again, these first two requirements are just some size estimates which are needed for the first and for the last estimate in the chain. What is very interesting is this condition 3. Also, as you see, well, depending on the context, this concavity means something different. Okay, so here in this setup, this function, this Bellman function must be locally concave. Locally concave, which means that it is concave along any line segment contained in the set. Okay, here's just one small comment. You see, this domain, right? This parabolic domain is not convex. So local concavity, like here, and the usual concavity is something different, right? Okay, so this is a slightly different thing. Okay, this is a very nice setup. One can study this local concavity condition. Maybe I will comment. Of course, the local concavity, okay, it is guaranteed if you assume that the matrix of the second derivative, okay, is non-positive definite. Okay, this is the concavity in higher dimensions. Okay, the nice thing here, so as usual, one assumes that the inequalities degenerate, so we obtain some very nice differential equation. When one searches for the Bellman function, okay, and this is a beautiful part of mathematics. This is the so-called Monge-Ampere differential equation. It plays a role in the theory of partial differential equations. Well, so this is a part there's a connection with a beautiful part of mathematics. Okay, here when one searches for this Bellman function. Okay, let me say, well, here is the Bellman function. Well, if one computes, searches, and so on, one obtains this function. Okay. Okay, I will not go into details here. Okay. The general philosophy is just like before. Okay. Okay, and the last part is devoted to extensions and applications of this result. Okay. Okay, so we discussed maximal estimates. We discussed these estimates for Martingale transforms or differentially subordinate martingales. What are the possible applications and what are the extensions of the method? Okay, so we start with extensions of the method. Okay, so first we discussed the discrete time context. Okay, we had just a sequence, right? It turns out that this method, it works perfectly also for continuous time processes. Okay, instead of inserting sequences, we just insert a continuous family of functions, sort of flow. Okay, so this works perfectly. So it can be extended to this context. Okay, so Bellman function for flows. Okay, whatever. The next observation is crucial. Namely, you see, in all these examples we discussed, we had two variables, x and y. We always had two processes which govern the whole picture. Okay, but in general, you know, there may be more objects involved. So this in particular means that these Bellman functions can be functions of 3 variables, 4 variables, 5 variables, many more variables. Okay, of course, the more variables, the more difficult things become. Okay, have to search for functions of 4 variables which have some sort of weird concavity, this can be really challenging. Okay, just one example maybe. So, for example, one can study the following estimate. So we consider Martingale F. We assume that G is its transform by a predictable sequence with values in -1, 1. Okay, as previously, and we are interested in the comparison, sharp comparison of the L1 norms. This is a very nice inequality. Okay, the so-called Davis inequality. Okay. Okay. So one can ask, well, for example, whether what is the best constant C here? Okay. So it turns out, you know, that this best constant is around 3.4. The Bellman function one needs to construct has 4 variables. And you know, well, it's I constructed this function for 2 years. You know, and so yes, I mean, you know, I was playing with these functions, searching for candidates, you know, and so on. And these candidates did not work. So I had this Bellman function on some part of the domain, but it failed, you know, and so then I returned and so on. So after 2 years, I managed to push all these things. You know that the Bellman function is given by 9 different formulas, 9 different domains. Okay, so the whole domain, 4-dimensional domain, is split into 9 parts, and on each part you have different formula. This is a horrible Bellman function. It would not squeeze into the slide. 9 formulas, very complicated. Yes. Okay. So so what I want to say that things can get really technical. Please keep this in mind. Here everything was quite smooth, right? These functions were kind of compact, but no. In general, these functions can be really crazy. Okay. And also, let me mention here that we discussed here the Martingale's taking values in the real line, but one can also study vector values case. For example, when these Martingales take values in Banach spaces. This leads to the so-called UMD spaces. Okay, unconditional for Martingale differences. It's an important space in harmonic analysis. Okay, and so there are many other extensions that I do not have time to discuss. Okay, and what are the applications? So let me give several applications here. So basically, the applications concern the boundedness of various classical operators in harmonic analysis. Okay, so there are many important operators in harmonic analysis, and their boundedness can be studied with the use of Bellman function method. Okay, so let me discuss well, just a few of them. So the first example is the so-called Hilbert transform. Okay, so the Hilbert transform is defined by the following. Okay, so if we have an integrable function on the real line, okay, then we consider this integral here. Okay, but one can show that this integral does not make sense, right? Because of this kernel here. This kernel makes this integral non-existent. Okay, that's why you have to integrate carefully. This is what this PV mean here. So it's a PV. It stands for the principal value. Okay, so this means that you do the following thing. Namely, you first integrate, right? You cut off the problematic region, right? The problematic region is where x and y are close to each other, because then this generates 0 in the denominator, which is bad. Okay, so what you do, you first integrate over the region where x and y are distant. Okay, so of course this integral makes perfect sense. There's no problem. Okay, and it turns out if you converge with epsilon to 0, then this limit makes perfect sense. Okay, this possible oscillations of this function, they somehow cancel out. This limit makes sense. Okay, and this limit is called the Hilbert transform. It has deep connections to the theory of analytic functions. Okay. Okay, so Hilbert transform is a one-dimensional object, right? It acts on functions on R. Okay, so there's a d-dimensional extension. Okay, and this extension is the family of the so-called Riesz transforms. Okay, so here we have some normalizing constant, right? Again, we have this principal value, which is the same as above. Okay, and here we have this formula. Okay, and here J ranges from 1 to D. It's easy to see that if you take D equal to 1, then this definition brings you back to the context of Hilbert transform. Okay, so we have some, well, these two strange operators. They are very important operators in mathematics. Actually, these boundedness properties of these operators, they have profound implications in the theory of Fourier series and many other areas. Okay, so these two operators are fundamental examples of the so-called singular integral operators. Okay, the singular integral, it means that this PV is needed, that the use of the principal value integral is required. Okay, and it turns out, quite magically, that the Bellman function method works perfectly here. Okay, it turns out that both this Hilbert transform and Riesz transform, they can somehow be appropriately represented by means of martingales. Okay, so we have this Hilbert transform or Riesz transform. You can go to martingales, and for these martingales, you have the Bellman function method. Okay, which allows very efficient control of various norms. So, in particular, we have the following theorem, which says that the norm of the Riesz transform is equal to the cotangent function. Okay, so this cot is cotangent, right? And here we have this angle p over 2 p star. Okay, p star is as previous. Okay, well, this is a dimension-free estimate for Riesz transforms. Okay, and it can be obtained by martingale methods, by the use of Bellman functions. And this also extends to some wider class of singular integrals. Another thing is that, well, here we have the action of the Riesz transform on the LP spaces, right? We go from LP to LP, but you can study other function spaces, so Lorentz spaces, and then the Bellman function method is also very useful.
Sorry, I have a question. I don't understand what happens if p is equal to 2.
Yes, if p is equal to 2, then this is p over 4, right? So cotangent is equal to 1, and the norm is equal to 1. And so this is correct. Everything is fine. Yeah. Another application, which is quite related to the previous one, concerns the so-called Berling-Alfors operator. So it is sometimes called the complex Hilbert transform. So the definition is quite similar to those previous. So those used previously, you see that here we have that this operator acts on functions on the plane. Okay, so we consider the complex plane, okay, with the Lebesgue measure, okay, and you consider this type of singular integral. Okay, again, the use of this principal value is necessary, otherwise this integral does not make sense. Okay, so this is a kind of a strange operator, but it turns out that it is extremely useful in the theory of the geometrical function theory. Okay, in the study of quasi-conformal mappings. So this is a very useful operator. In particular, the question about the boundedness properties of this operator are very important. Okay, and there is a celebrated conjecture by Tadeusz Iwaniec from 1982, which says that the norm of this Berling-Alpos operator is equal to p star minus 1. Remember, this is exactly this constant for the LP estimates between Martingale transforms, right? This is the result of Bruckholder we discussed previously. Okay, so well, this is a very nice conjecture, and it turns out that, well, this Berling-Alpos operator, well, it can be somehow controlled by means of martingales, okay, or Martingale transforms, okay, but unfortunately there is some sort of small tiny error, okay. Previously, for this Ries transform, Hilbert transform, okay, this error vanished and we obtained the norm of the operator, okay, so we obtained the sharp constant, sharp inequality, okay. Here, well, here it's problematic. Well, this conjecture is still open. Anyhow, well, there is some progress. Okay, so you see here we have with 1.4, and you know, actually, let me say a few words more. So this related result was proven. The first result in this direction with this nice form of the constant was obtained in 1996. Okay, and it used here the constant 4. Then it was improved in 2001 to 2. Then it was improved to 1.575. Then 1.4. And you know, it's the world record so far. Okay. Okay. And well, this is the last slide actually. So the third type of applications. So it concerns the estimates for classical operators. So this is just a little bit informal slide. So generally, you see the situation is like this. Many classical operators in harmonic analysis, okay, like general singular integrals, fractional operators, square function operators, many classical operators can be discretized appropriately. They can be approximated by certain discrete operators, right? I mean, these classical operators are typically expressed by means of some integrals and so on. They are of continuous flavor, okay? So what one can do when one studies such continuous operators, one can consider their discrete versions, okay? And these discrete versions are so-called sparse operators, dyadic shifts. This is kind of new technology, I would say, and it's quite fashionable in the recent literature. It turns out, of course, one can ask about the methods of studying these sparse operators in dyadic shifts. And it turns out that the Bellman function method is a very, very efficient player here. Okay, so these objects can be studied with special functions. Okay, and just a sequence, just a sentence is that in particular one can study weighted estimates. This is another huge area. So actually, this is one slide, but it's a huge subject. Okay. All right. So well, here's some small literature on the subject with some monographs, and that's it. Okay. Thank you very much.
Well, any more questions, comments? We have time. We have finished earlier.
Yes.
I have one more question.
Okay, please, and then one.
So this Berling-Alpos operator is unbounded in the case when p is equal to 1?
Yes.
Okay.
Yes, one can construct some examples. Yes, 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 yes. There's always this problem with this boundary endpoint problems. L1 and infinity. There's always this explosion of the norms. Yes, one has to study some substitutes, like some weak type estimates or some BMO estimates or something like that. Yes, we do not have boundedness in this boundary case. Yes.
Okay, thank you.
Okay, Błażej, please.
Thank you. So about the Swiss transform. So for the single Swiss transform, this Martingale approach fits exactly the norm. But there is another conjecture of Ibanez and Martin about the vector of this transform. I wonder what is the obstacle that the Martingale method does not fit the conjectures norm. Do you know why is it that? Because I use it for the just for the single, why doesn't it use for the vector? I don't really understand.
Well, so actually, well, the answer is that, well, this approach using martingales and Bellman functions, it does not give it does not seem to give the best constant for this, well, vector of Swiss transforms in two-dimensional case, in multi-dimensional case. The reason is, in a sense, is similar to the reason for the Berlin-Karpus operator. It actually, it's the Martingale methods do not work for p equal to 2 even. There's somehow the reason that the situation is like this. So if you have this Berlin-Karpus operator or you have this vector Swiss transform, if you try to somehow represent it using Martingale transforms and things like that, you somehow lose too much. That's the answer. Even for p equal to 2, right? Because then you have this constant 1 for obvious reasons. But these Martingale methods, they just somehow create some error which cannot be removed. So at least so far.
Okay, any other questions? Comments, please? Please? There are questions on the chat.
Okay, there are questions. Yes, there are. Okay, thank you for the talk. Thank you for the talk. Thank you for the talk.
Okay, so no questions.
Okay, you're welcome.
Okay. Well, okay, so we may finish the morning session. Stop. Yes.